Thank you, Matt. So first of all, before starting my presentation, I would like to thank you for the organization of this conference and also for giving me this opportunity to talk in front of so many people. I will have a short introduction about myself, so I'm not going to talk about myself now. I simply want to introduce the topic of my presentation today, which is going to be about on how to combine knowledge acquired from multiple fields to achieve efficient and non-invasive crowd control. And this is the outline of my presentation. So I will have a very short self-introduction. And for most of the time, I will talk about my research from the starting point, which has been the study of the bidirectional flow, and how I eventually found a way to define a measure for congestion of crowds, and how I'm trying to turn my research into a more like cognitive or like aspect to achieve a better crowd control. And toward the end of my presentation, I will turn a bit political and look at the past of research on crowds and what are the trends and the needs, in my opinion, and conclude with some take-home messages, which are my point of view on the crowd research. So to start, a few words about myself. I'm originally from Switzerland. You may know that it's divided into different languages. I'm from the south of Switzerland, so I'm the Italian-speaking region, as you can guess from my accent. But I later moved to Zurich to study mechanical engineering during my bachelor, and I later did a master in nuclear engineering as I wanted to combine physics, more theoretical aspects, with engineering. After that, I moved to Japan. The idea was to do only a short internship for 1 year in a private company, and I eventually decided to stay a bit longer as I liked Japan and the language and the culture, and that turned out to be 3 years more. And I liked working in a company, but I wanted to do more like fundamental research. I wanted to do more academic research. So I quit my job and I went to the University of Tokyo under the supervision of Professor Nishinari, where I did my PhD project, which finished in 2017. And after that, I've been staying in the same position, doing research in crowd management, which I'm still doing now. So giving a very short overview of what I did so far, not going into detail. So during my master thesis, for example, I did a study on the fluid dynamics inside jet turbines. While during my master thesis, I've been working on the measurement of the gas composition inside nuclear reactors. And when I was working in Mitsubishi, I was actually doing simulation of mold flow, so polymers, plastics. So they may look very different, but if you look more in detail, they share in common that it's all about like studying something moving, some fluid, some sort of fluid. And I have to say that I've been always interested in mathematics and physics and so on, but from my old days, so as I was a high school student, I also liked social science and the humanities, philosophy and psychology and so on. So I always try to find a way to combine social science with like physics and mathematics. And as I've been also working in a private company, I want to do something which has some application. And it was when I moved to Japan that I actually noticed from the countryside, so we didn't have many people. And it was when I moved to Japan that I seen that like actually it is not only like air or like water which flows, it is only people. So you can have flow of people, you can have people waiting up in the bus stop, and so there are people everywhere. And I got interested in a way to study the flow of people. And I actually discovered that in fact there is something which is called pedestrian dynamics, which we all know, which is an already well-developed research field. And so I decided to jump into this new field and to do my research. And from now on, I will talk about what I did as a researcher. So the starting point for my research has been the bidirectional flow. What is the bidirectional flow? That is very simple. Is when you have people working in two different directions and they eventually make lanes or not. And that is very common. So you can have it in a corridor, in a sidewalk, in a crosswalk. So you can find it in every pedestrian structure. It is very common, but it's also very important because it is related with some of the accidents which happened in the past. For example, the Phnom Penh accident, which happened in Cambodia, or like even the Love Parade accident was somehow related to a bidirectional flow. So it is very simple, it is very important, but still there are quite many parts which are not completely understood. And to to be honest, one of the reasons why I started doing research on this particular topic is because when I joined the lab as a PhD student, there was already an ongoing project to study the motion of people inside a subway station. And the subway station that we studied is given in this picture here. So there are two train lines running vertically, and there is one train line which run horizontally. So basically, there is no people changing platform from the both train lines running vertically, but you have many people which either move from the area A to area B, or in the opposite side from area B to area A. And when they do, there is always a big crowd in this red area, which is a sort of a corridor. So what we did is to measure the flow of people every time a train arrived, moving from one direction to the other, and trying to plot the results to understand how is the motion inside the corridor. So these are the results, which I'm going to present a bit more. So on the x-axis, you have the flow of people from B to A, and the y-axis, you have the flow of people from A to B. For example, if you take the circle here, it means that there were only people moving from one direction, so that is a purely unidirectional flow. While the circle in the middle, there was always people moving from both directions, so that is a quite clear bidirectional flow. And we didn't only measure the flow from both directions, but by using the information from the camera and also some criteria that we developed, we also categorized the way in which people moved. And we had three different criteria. So one is the free flow, which means that people were able to move as they wanted. So they could turn right, left or right at any time. They didn't have to care about the people around them. And in some conditions, people were able to keep a stable speed, so they didn't have to slow down, but they had to move in lanes to avoid collision with other people. So that's what we call the motion in lanes. And in some other conditions, we observed that people were not able to keep a stable speed, so they had to slow down, they eventually get stuck, and they had to move through the opposite crowd to go to their destination. So what is interesting is that if you try to set a line dividing the area in which people were able to move in a stable way and the area in which people were not able to keep a stable speed, you can actually not draw a straight line. This is because we know from the literature that the unidirectional capacity is about 2.2 people per meter per second. So if you want to draw a line, this is not possible. So you have to use some kind of curves to set the boundaries between the different kind of motions. But from now on, I will talk in a different, using different language. So I will not talk about flow in different directions, but I will use the concept of flow ratio, which is the ratio between the flow in one direction divided by the total flow. So if you have 0 or 1, that is a purely unidirectional flow. It means people are simply moving in one direction or the other. When we are around 0.5, it means that you have the same amount of people from both directions. So that's a purely bidirectional flow. And everything which is in the middle is either a big group and a small group, or a big group and a small group on the other side. And if you try to set the capacity for the bidirectional flow, which means so the maximum flow that you can have for each flow ratio, which can be kept for a long time period, you can see that we have a sort of U shape. So in case you have the same amount of people from both directions, the capacity is lower than in the unidirectional case in which you have people only from one direction. But what is interesting is that when I wanted to check my results and to compare them with the literature, I found that in fact there are different shapes given by different studies. So somebody claimed, like in our case, that the capacity for the bidirectional flow should be a sort of a U shape, in which the case in which you have the same amount of people from both directions is the worst. However, somebody claimed that if you have people working from two directions, they will eventually make lanes. And once lanes are made, it is not more bidirectional flow, but it's many unidirectional flow moving into each lanes. So I was a bit confused on what is the correct answer and how should we which number should we use to define the norms used in evacuation and pedestrian traffic. So In that case, we need to use a consistent value, a conservative value, and to define that, we need to understand what is the shape of the capacity and why we have these sort of different shapes. And to study this aspect a bit more in detail, we organized some supervised experiments in which we had 54 participants working under different conditions. So in one experiment, we had all the people working in one direction, so on the unidirectional flow, and then being gradually increase the number of people coming from the opposite direction to create different sorts of flow ratio. And so the last configuration that we tested, it was when we had the same number of people from both directions, what is called the balanced bidirectional flow. And after doing the results, after obtaining the video and making all the tracking, I was expecting that one configuration will be faster than the other. But when I checked the results, I was very disappointed because there was no difference in speed between the different configurations. So the unidirectional configuration was as fast as the bidirectional configurations, and it didn't matter on the flow ratio. We always had more or less the same speed. What is a bit interesting is that you can see some increase in the variance, but still there is no statistical difference between the results. And by looking again and again the video, I found out that I was wrong actually in calling my experiments bidirectional, because in fact, in the beginning, people, they are just simply working straight. So there is no bidirectional flow in the beginning. It is only after this point that people start really interacting. They need to make lanes. And when lanes are made, people they actually have to only follow the people in front of them. So that is very simple. And since the groups were not very big, after people pass through each other, they have space on the left and on the right. So the lanes get dissolved. And at the end, they can simply work straight again, as in a unidirectional flow. So we show this video once again. So at the beginning, people simply work straight. There are very weak interaction. And it is basically after this point that the interactions become very weak. People move to the left and the right, and lanes are made. And once they are made, if lanes are made, it is very simple. They simply have to follow the people in front of them. But at the end, the lanes will eventually dissolve, and people will keep working straight again in the last part of the experiments. And also when I was trying to find a way to analyze the results, I understood that so the speed was not a good indicator, and also density was not good enough because we always had the same number. So I needed something which could explain better the smoothness in which people move. And by looking the video again and again, I had an idea. Since I've been working on fluid dynamics, I know that like when you have a very slow wind, so when you have some kind of laminar flow, as we call it, so you have this kind of weather with very beautiful clouds. But when the winds start to be a bit stronger, you have this kind of wavy clouds. And the most dangerous case you can have in weather is when you have a complete rotation of wind, which can form, depending on the scale, tornado or typhoons. And if you compare the videos from the crowd dynamics from people, from crowds, you can see that you have something similar. So when people walk in one direction, there is basically no oscillation, so there is no turbulence somehow. But when you start having different directions, people have to move to the left and the right, and you can see some kind of like a oscillatory movement. And for example, this is the video that was taken by Helbing during the accident in Mecca. And you can see that you really have some kind of turbulence inside the video. So my idea was that if the concept of rotation is the cause of instability in weather, maybe we could use the same approach to explain the smoothness or like the stability of crowds. So I analyzed the experiments by taking the different phases I've been presenting before, and by measuring the amount of rotation, so what I call the rotation range, in each different phase and for the different configurations. And these are the results. So for instance, if you take, for example, the unidirectional configuration, which is the triangles, you can see that it was very stable during all the phases. So very low rotation, very stable, and people moving in a very smooth way. Also, if you look at the bidirectional configuration at the beginning, And at the end, when they were simply moving straight, you can see that, in fact, that is a purely unidirectional motion in a way that you have a very low rotation, you have a very stable motion. And also, if you look at the lane formation, lane dissolution, which is only in the case of bidirectional flow, you have a high level of rotation, which means that in that case, you have a high instability, which is expected when people have to make lanes because they have to move from the left and the right and try to find a way through the opposite crowd. But the most interesting results is when, if you look at the moment in which people were able to make somehow lanes, you can see that for the balanced case, so when there was the same number of people from one direction, it has a very low level of rotation, which means that when people in the balanced case are able to make lanes, it is in fact simply a number of unidirectional flows moving in opposite directions. So it is very stable. People are very effective in moving, while when you have a big number of people against a small number of people, so lanes probably are not able to form. And if they're formed, they're not very stable. And so after seeing these results, I went back to the literature, and I've been checking more in detail about which kind of studies were the one I've been presenting before. And I noticed that all the studies that were presenting a U shape for the capacity, they were all what I call cross-type experiments. So it was always a small group of people crossing through each other and going to the opposite direction. So that is very common, for instance, in a crosswalk. So if you have people waiting in front of a traffic light, usually the number is not that big. And also there is not such a big distance between one side and the other. So they have a very little time to interact. And usually the number is also quite similar. So in that case, if you have the same number of people, it is very difficult for both groups to understand whether they should turn left or right. And also they have to check in the people on their side. So in that case, it's very difficult in the case you have the same number of people. While if you have a dominant group with a big number of people against a small number of people, they can dominate and impose their motion to the other group. However, eventually after some time, if you have people which keep moving in a corridor, like a corridor connecting to train station, if you have people from the morning to the evening passing through the corridor, lanes will eventually form maybe in the morning. And if people can keep flowing, in the case in which you have the same number of people, it will become somehow the most efficient configuration. So I developed a function which can express the transition from one side to the other, and by using a single parameter can represent the capacity before and after lane formation. And also because, so I had some encouraging results by the use of rotation, by the use of rotation to explain the stability or the smoothness of pedestrian crowds. Based on that concept, I developed what I call the congestion level, which I'm going to explain in detail. So the idea is basically I still use the concept of rotation, but I developed it in an algorithm which allow you to represent congestion both in time and in space. So I will explain this concept by showing this video. So in this video, it's going to be an experiment of bidirectional flow as well, but in a circle. So you have people working in a clockwise direction and people in a counterclockwise direction. And in this video, the most congested area will be shown as red, and the non-congested area will be shown in white. So now starting the video, you can see that there is no congestion now because people are not moving. And as they start moving in the places where people are interacting, you can see that it becomes red because there is some high level of congestion. But after people make lanes, you can see that there is no red spots anymore because people are organized, they are smooth, they're moving in a very smooth way, so there is no congestion anymore. And this is also clearly seen in the graph in the middle, which is showing the maximum congestion level in this area. You can clearly see that after people were able to make lanes, there was a drop in congestion. So this is clearly something which allows you to see this kind of phenomena. And it was interesting because when we checked the speed of the experiment, it was very constant. And also the density is the same because you have the same number of people. So this is really a property which allows you to see something which is not possible to be measured by speed or density. And recently I've been taking the concept a bit further and also doing some cooperation with other researchers. So, for example, a work which I did with Francesco Zallungo, who is a very good mathematician. So he wanted to take my congestion level, but making a more like physically sound. So making a number, unitless number, which is from 0 to 1. And so he made a very good, very sound mathematical definition. And we also test a paradox, which is the video given here. So in this video, you have people crossing from 2 different directions. And so in this case, the density is very high. So you will expect that people have to slow down because you have a high density. If you take the fundamental diagram, in this case, you should have a very slow speed. But since people are not colliding, when we measure the congestion number, it turned out to be 0. So that is a kind of like a example which show the different properties that we are measuring using this property. And also something that I did with my colleagues in Spain, Iker and Angel. As you probably know, they did some experiments on the effect of the obstacles during evacuation. And we applied the congestion level to understand how the obstacle changed the overall motion of people. And the results showed that when you have no obstacle, you have the area of maximum congestion just in front of the exit. But when you place an obstacle, basically, the condition is not changing in a way that you simply you simply shift the area of maximum congestion from the location in front of the exit to the location between the obstacle and the exit. And that was actually the case only for high competitiveness. So so far I've been talking about like physical approaches to analyze crowds. But as I said, so I also like social science, and I'm trying now to change a bit my direction of research, by also including some cognitive aspects, and also trying to address problem in relation to crowd control. And in this aspect, I've been very lucky to meet Murakami-san, who has been my colleague for 3 years, I think. He unfortunately left last year. And he has been working for many years on animals, especially on crabs. And when he joined our lab, he has been very interested in the results I did on the bidirectional flow. And he wanted to get my data and to analyze them. And what he did is to do the analysis, which is very common in the case of animals. So he checked the distribution of sidestep in the case of humans in the experiments of the bidirectional flow. And what he found out is quite interesting. So he found out that before making lanes, people perform what is the so-called levee walk. But after lanes are formed, the levee walk disappear and people start making a different kind of motion. So what is the meaning of this result? It is very interesting because levee walk is observed in animals when they're looking for food, and it's a very efficient way of moving into space. So I don't know if that is something related to animal behavior or not, but it's interesting to see that we share some kind of motion only in specific moments with animals. So it is probably something which has come from our instinct. So I don't know. And inspired by these experiments, we also had the idea to move like into more cognitive aspects. And we also studied, we repeated the same experiments by having some smartphone. So we had the same experiments, but the 3 people in the front here with the red caps, they were working by using a smartphone. So as you can see, probably you may remember the video I showed you before. So as you can see, it was more difficult for them to make lanes, and they also almost bump into the people from the front in front of them. And in this experiment, we checked 3 different conditions. In one case, we had the people with the smartphone on the front. In one case, we had the people with the smartphone in the middle of the group, and in one case, we had the people with the smartphone at the back of the group. And these are the results. So what we found out is that compared to the baseline in which there were no distracted pedestrians, When the distracted pedestrian were at the front, it took more time to make lanes because people were not able to communicate themselves, were not able to mutually communicate, and this affected the lane formation and it had an effect on the overall crowd. While when the distracted people were on the back, didn't have much an influence because uh, they were not the one responsible for making lanes for the lane formation. And also, what we found from the experiment is that the reasons why the distracted people affected overall crowd behavior is that because there was no mutual communication with the counterflow, in a sense that in order to have an efficient self-organization of crowds, people have to somehow communicate their future position to the other people, and other people need to understand their future position. So that has to be a mutual mechanism. And when it is only one-sided, because somebody was distracted, that is going to affect overall crowd behavior. And for some reason, this research got much interest, so we got highlighted in the New York Times. But what was more funny and more interesting for me is that you may know, we also got the Ig Nobel Prize for this research. So I'm very happy of this. And so I've been saying that I wanted to move a little bit more the cognitive side. And after all, defining different measures to quantify pedestrian crowds, so quantify, for example, congestion, I also understood that even if you have information on crowds like density, trajectories, origin, destination, whatever. So we had a keynote speech yesterday showing how they collected so many data in Mecca. So if you have a lot of data, you really need to understand how to use this data to change the behavior of the crowd, so to control the crowd. And I found that there is little research which is done in this direction. So actually, some of the question that we need to answer in this frame is, for example, which information is effective to control the crowd? So which method is the best one? And which kind of information and how is received by the crowd? And also, if you want to target a specific population, which population should you target to achieve an efficient crowd control? So we performed a simple experiment. We had a loop divided into 2 lanes, and people had to walk in one direction. And there were an inner loop and an outer loop, and people were able to change the loop only in 2 positions, given here as a lane change. And also we had some sensors in 4 different positions, which measure the speed of pedestrian in real time in the inner and in the outer loop. And in the middle, there was a big wall, so people were not able to see to the opposite side of the loop. And using the information from the sensors, we show the current speed to the pedestrian. So when they were working, they were able to check the monitors and see whether the inner loop was faster or the outer loop was faster. And also, we had some human guidance. So we had some students providing guidance to the participants under certain conditions. So participants had to follow the guidance given by human position placed here. So this is a video from the experiments. So you can see at the beginning there were a lot of people in the loop, and after a certain time, people were allowed to perform lane change, and of course they wanted to move to the outer loop because it was faster, because it was less congested. And after a certain time, they reached some kind of like a stable condition in which the speed is more or less the same in both loops. And these are the experimental conditions of the experiments. So we had, as I showed in the video, 35 people in the inner loop and 5 people in the outer loop. So people had to move they had to change position because that was not acceptable to them. Also, we gave the instruction to move as fast as possible. Of course, this is always difficult in control experiment, but okay, this is the way we did it. Probably there are better way to motivate participants. And each experiment had a computer programmed start and stop time. So each experiment was exactly 3 minutes. And what is also important, in these experiments, we didn't simply measure the speed of the participants, but after each trial, we asked them to answer to a questionnaire in which we asked on the comfort perceived in that particular condition. So after each experiment, participants has to write down on paper whether they feel comfortable or not. The condition so the experimental variables that we tested are in regard to information provision and human guidance. So in information provision, we gave 3 different kinds of information. So in one case, there was no information at all. So there was no monitor. People simply had to work and to decide to change lane or not, just based on their vision. In some other conditions, so we show the information as given here. So we show the speed, the current speed, the real-time speed, and people had to or could decide to change the loop or not based on the information given to them. Also, in one condition, we use some simulator to do some real-time prediction of the future speed, and we showed this speed that will occur in the future. And also in some experiments, we had human guidance, so we had some students providing guidance to the participants, telling them to move to the inner loop or to the outer loop, or just move straight. While some other experiments, people had to decide by themselves whether to stay in the same loop or to move to another loop. And these are the results from the experiments. And what is very interesting is that if you look at the configuration which had the highest flow, so we checked the total transit of people in the 3 minutes. If you check the configuration which had the highest flow is the one when we showed the present speed to the participants. So that is the case in which people were able to move faster. But if you check the configuration which had the highest perceived comfort by the participants, is when there was no information at all, and there was the staff providing guidance to the participants. So the staff was using some kind of remote controller to tell to the participant to move to the left or the right or keep straight. And when I interviewed some of the participants at the end of the experiments, I understood that the reason why they felt more comfortable when there was human guidance is because they didn't have to check at the monitor all the time and decide whether the speed was highest or lowest. So they didn't have to be stressed to check the information. And also, they didn't feel like they were controlled by the machine, but they knew that there was some people behind the control. So that was very interesting, the fact that even if you have some kind of data, some kind of feedback that you get from sensor on the crowd, it is usually better to have some human behind that, because that is better perceived by the people inside the crowd. Also, an experiment we performed, I think 2 years ago, it was with a wheelchair. And so one of the questions that it came out when designing this experiment, so usually even if you give information to the people, you never have 100% compliance. So some of the people will not comply to your information, to what you tell them. So if you want to achieve the best performance in crowd control by making the less effort, so which kind of population you should target to achieve good efficiency. And in this experiment, as I said, we used participants in wheelchair. We designed a room with 4 different exits, as given here. And each exit was covered by a curtain, by a black curtain. So when the participants were inside the room, they were not able to see the exit because there was the black curtain here. And each exit had a different feature. So there was one narrow exit, there was one wide exit. One exit has a sort of oblique path. So people in wheelchair had to change their position and they couldn't go out straight. So it took a bit of time for them to leave the exit. And one exit has a step, so people in wheelchair were not able to leave from that exit. And also we provide a map to participants, which was allowing them to know the kind of exit behind the curtain. So for example, we told them, so okay, now we are going to test the experimental condition number 1, and participants could look at the map and they knew that, for example, the east exit is not allowed to wheelchair users. The west exit is wide, and the north exit is narrow. But we tested 3 different conditions. So in one condition, nobody knew which configuration was tested. So people had to open the curtain. They had to check by themselves. They were not able to know the kind of exit which were prepared behind the curtain before the beginning of the experiment. In one condition, we only told to the people on wheelchair which configuration was tested. So people on wheelchair were able to look at the map, and only them were able to know, for example, that the east exit in configuration number 1 was not open to them. And finally, in the last configuration, in the last condition, everybody got information on the exit. So everybody was able to check the map, and everybody was able to knew on the position of the exit before the beginning of the experiment. So this is a video of the experiment. So you can see that everybody has a paper in which we gave the different configurations. And in this case, only people on wheelchair were informed on the location of the exit. So as you can see, people on wheelchair, they knew that some exit was not possible to them. So they moved straight to the exit, which was more comfortable for them. And these are the results from the experiments. So what we measured is the egress time, so the time it took for the people to evacuate. And as you can easily expect, so when everybody was at the information on the exit position, the egress time was about 22% faster. So of course, if people know that one exit is wide, they will try to move to that exit. But what is interesting is that when only people in a wheelchair had the information of the exit, so only 3 people out of 52 had the information about the exit, in that condition, the egress time was already 18% smaller than in the case when nobody had information. So that means that if you give information only to a small number of people, which is very effective in having an influence on the whole crowd, you may achieve the same result that you would have by informing all the people. And in our case, so what we found out is that if you inform vulnerable users, of course, that is very good for them, because for people in wheelchair, it's very important to know where there are stairs, where there are exits which cannot be used. But that is also good for the whole crowd. So that is something which has to be keep in mind, that if you want to inform all the people, it may be better to try to target on the user which has some kind of disability. So from now on, I will turn a bit political, and we'll try to give an overview on the past research on crowds, to highlight what I see as the trends and the needs for the research in the future. So this is a short timeline, or a timeline for the research in the last century. This is possibly wrong, so I'm sorry if I did something wrong. So what I want to show you is a bit that there have been different waves of fields having a strong influence on crowd research in different time. For instance, so one of the first studies that we know on a crowd is probably the one of Lobon, which probably one of the first that really introduced the concept of crowd and how people can influence themselves behind their individual identity. But it was probably only about in the 50s or in the 60s that we really started to see sociological approaches to try to explain how we have shared identities, or what Anne explained yesterday. So all these kind of theories, I think they started in the 50s and the 60s, and then of course they have been developed since then. So at the beginning, crowd research has been mostly a sociological approach, a social science approach. But probably because cities started to grow, and there was the need to build some new neighborhood in the outskirts of the city, and to build them very quickly and very fast. So even engineers and like urban planners and architects and designers probably had the need to define some measure for pedestrian traffic. And you can see that in the 60s, you have a lot of studies in that direction, like the Book of Hall, which try to define the proxemics, or like the personal space. The level of service by room is from 71. And during the 70s and then the 80s, I think there are quite many studies trying to really get numbers on crowds on pedestrians. And for instance, if you there is a very nice work by Weidmann, unfortunately or in German, which really gave a collection of all the measures, all the studies which has been done in the previous period. And in the 90s, the computer started to be quite powerful, so it was possible to start doing simulations. And that has been there has been a trend of like many simulation models developed from that moment on. So, for example, the social force by Helbing is from 95, and after with the turn of the century, there has been an increasing number of control experiments, and that has been even faster. So the increase after the introduction of tracking softwares like the MyTrack by Mike. And also in the last 10 years, there has been a boom of like a solution to perform real-time tracking or like real-time sensing of crowds. So this is just my outline for like the crowd research in the last century. So it has really, in my point of view, sort of different waves with different disciplines having a strong influence on a particular period. So in this slide, I want to present something different. So it is work that I'm currently doing with Agani and Corbetta, which I expect to publish probably next year. So we analyzed a crowd accident to try to find some pattern, try to understand how it changed over time. And something that is interesting is if you observe the graph on the left, that is the number of fatalities in the crowd accidents which occur from the beginning of the century. And you can see that you have a peak in the 50s, and after there is a decrease, and then you have an increase because the world population really increased at that time. So it is somehow expected that you have more people, you have more accidents. But this decrease is quite interesting because I believe that is what the knowledge on like crowd behavior had benefited. So as I said, in the 60s, there have been a number of studies which try to quantify crowd motion, which started to make norms. And I think so that has been very important in decreasing the number of accidents. But if you look at the countries where the accidents are getting more common, you can see that today's most of the accidents occur in developing countries, so in countries which are classified as lower middle income. So that means that we have a lot of knowledge on crowd behavior and crowd management, but we also need to share that knowledge with people that are more in need. And so this is the last slide on somehow my political side of like crowd science. So this is what is generally believed the concept of crowd control, which is said to be a 5-stage process. So I start from the left. So when you have like an empty train station, it is usually only needed to give information to the crowd. So even if there is no people, you need to have like signs in order to have people not to get lost. So this is what we call the wayfinding, which is usually made by people in the design or architecture department. And if you try to influence the crowd, so that is if you want to have somebody moving into a shop, that is basically what is done in the frame of marketing, which is basically related with psychology or economy. So I now move to the other side. So when you really have a violent crowd or like a very dense crowd that you really need to take under control, in that case, you need to enforce decisions. And that is basically crisis management, which is related to psychology, but also with law. So you need to know if you are allowed to use violence, so people arrest them or not. And when it comes to steering crowds, so to change the flow lines, or like to change the way people behave in a physical way, that is probably related to physics or like computer science, because you need to make simulations. But I think when it comes to guiding crowds, we really need to cooperate, because it is really a field in which you need to have like the cooperation between the different fields. So I think VR is probably an increasing it's getting an increasing role in this part. But still, I think that the cooperation is really important in that regard. So take-home messages from my presentation. So as I said, I believe now there are many ways to quantify, evaluate, and analyze crowd behavior. And there are different ways to measure the way pedestrians move using sensors. And also crowd simulators are getting very common in the design and prediction of crowd motion. But I think if we want to find a way to get the data and try to change crowd motion in a practical way, I think that is really where multidisciplinary cooperation is needed, as Anne already said yesterday, and I really agree with her take-home messages. So to conclude, I want to give a short advertisement. So I've been writing a book on crowd management with my colleagues, especially with Professor Nishinari, which is about to get published next year, probably in January. So I think most of you already know what is written inside, so it is not something new. But if you have some student that is probably coming to your lab, which is approaching the new field of crowd management, so that can be probably interesting to them. So give a look. And so this is the end of my presentation. I really would like to thank you for the attention, and you may ask any question now.
Thank you very much, Claudio. Well done. Great presentation. A good summary of what you've done over the past few years, and a good outlook for future. So, floor is open for questions. Let me see. I think there is one question. Oh, questions are coming. Okay, so wow. Okay, so do you want to read the questions yourself, so it might be easier for you to grasp them? Maybe start with Hantao.
Yeah. So much important. Yeah, I think that is related with the limited. So I think technology is not bad. So I'm not saying that simply giving information to the people with some display is bad. Is not bad, but so I think it is important for people to know that there is somebody evaluating the numbers which are behind. So it is not simply given by a computer, because I think that it will help making them more comfortable. So I'm not saying that you really need to have somebody physically inside the crowd, but I think it is really important to have the perception that there is somebody behind. So it is not really, I'm not saying technology is bad. So I hope I answered the question. And moving to the next one.
Yeah, the next one is from Christina asking, I have a question to the wheelchair experiment. The experiment, the participants are in the same room. I'm wondering whether the participants follow the instructions only because they can see the wheelchair, so the wheelchair users justify the instructions. I'm wondering what happens when the wheelchair users are hidden by a wall. Can you elaborate on that?
Well, it is possible that, so actually we gave instruction on a smartphone, and so people were able to see the experiment number on the smartphone, and we asked them to keep the smartphone as close as possible to their eyes, so that other people were not able to cheat. And it is possible that people were able to see the answer, or were able to understand that the wheelchair users had the information, but I think that was not an important factor.
Okay, so let's move on to the next one from Armin. Thank you. I have a question about the first slides. If I understand it correctly, your results on capacity in bidirectional flows are not related to a steady state. For example, the results are not independent of the initial conditions. Can I get even higher capacities or other flow ratio functions if I choose very special initial conditions?
Yes, I think, for instance, like in the experiments you had in Jülich, I don't remember, maybe 10 years ago, in which you had people moving to the left and the right. So that it was a very special initial condition in which people had to go in a specific direction. And in that case, you can have a much higher flow. So I think it really depends on the condition you have, the instruction you give to the participants, and also what, for example, if you have like people from countries which are used to move to the left and people from countries which are used to move to the right, so in that case, probably it is not going to work very well. So I think so. My experiments were really the fundamental, like how can I say, mechanism which is used by people to like self-organize. But then there are like much higher like consideration which has to be done on how people navigate. So I think
before we move to the next one, I comment on that. We are actually trying to build. We're building a sidewalk network model for pedestrians, trying to model the movement of pedestrians in the urban context. So not a building, it's actually a network of sidewalks. And sidewalks are bi-directional. And we were actually looking at your bi-directional capacity estimation methods. And then in connection with Armin's comment, in an uncontrolled environment like a real sidewalk in a city, any kind of lane could form. Sometimes people form dynamic lanes that they're weaved into each other. Sometimes they really nicely separate on left and right of the sidewalk. So I think it's a challenge to really understand what the initial conditions would be. So yeah, anyways.
Yeah, I agree.
So
I was just reading the question.
Let's move to Enrico's question. In your overview of history of crowd research, you did not explicitly mention virtual reality as a tool for crowd research, which has impacted the field. Why is this the case? Is it about the need to test more the validity of the data produced, or because of its potential against our methods?
So yeah, that is a very good point. Well, I think one of the reasons I didn't mention about VR is that, so I haven't had the opportunity to work that much about VR, so I actually forgot to mention about it. So I think it is important. And also maybe one of the reasons is that, so probably VR is starting to be important now for the research on crowds in a way that until now it has been mostly used for like route choice or like this kind of like how people behave in a different environment. So it was not really a method to evaluate the self-organization of this kind of motion, because it was very difficult to have like how can I say, many people moving with their avatar, so inside the crowd. So I think it is true that VR is playing a very important role. As I said, I think it is going to play an important role, but probably I think the VR methods that have been used so far, they are probably a bit different to what I perceive as crowd research. So I think now that it is possible also to have people moving, like really working on like a step mill or these kind of things, I think that is really a moment in which VR can play an important role.
Yeah. Thank you, comment from Christina. Nicola is also just thanking, I guess. Looking forward to your publication on crowd accidents. Sure. I think Nikolai also has a question.
Yes.
Question on the levee walks. If I remember correctly, the distribution of step sizes in levee walks is a scale free with a heavy tail. Realistically, in pedestrian systems, this distribution should be truncated as the systems are finite in size. This has been discussed at length in the animal behavior literature. What are your thoughts on this? Is the levee walk really relevant?
Well, to be honest, so I'm not the first author of that paper, so I understand the general discussion, but so I'm not an expert on this kind of works, like Brownian work, Levy works. So I'm sorry, but I will have to relate that
That's
question
okay.
to Murakami-san, who is like the expert on animal